Okay, so Nevine is a senior applied scientist at AWS Cryptography. She works on AWS cryptographic library of AWS. Like again, given the scale of AWS, I don't need to convince you that any processor cycle counts. So one of the focuses of Nevine is algorithm development and machine level optimization for AWS. And also, like, of course, like Amazon doesn't want to run just any cryptography. Like, you have to kind of just implement something because it's faster, and so that's why AWS LC is 6.143 certified. And this sometimes comes at attention with speed and security guarantees, and so they will tell us about some of this, like the direction AWS is moving.
Okay, now good morning, everyone. Thanks for the introduction. My name is Nevine Ebeid. I'm a senior applied scientist in the crypto team at AWS. This is joint work with Thanos, Shai, and Matt. And there is an ePrint manuscript that we posted just shortly before the workshop that you can see more details about it. So what I will talk about is the title, but come to dissect it. So, Blockcipher-Based key commitment for nonce-derived schemes for symmetric crypto. We'll see. Hopefully, everything the right steps. Okay. So we'll talk about nonce-derived schemes, some existing ones, key commitment, what basically might be needed. An existing one that we'll focus on is AES-GCM, and we'll see how we apply key commitment. As Nikhil mentioned, FIPS compliance of that scheme, some data limits, and security analysis and performance numbers. So the authenticated encryption with additional data schemes like Ebeid, you know they are prevalent. We use them like in data in transit, like in TLS, such as AES-GCM and and we use them in storage. So, but they have their challenges, and we will talk about them. One of them is the small number of messages that can be encrypted per key. This is fine for a small application, but when you're talking about the cloud, this becomes really a challenge. They are vulnerable to attacks if IDs or initialization vectors are removed. And they also have no key commitment. We will come to show more about that. So nonce-derived key schemes address some of these issues without increasing the block size. So like we can always say, okay, let's go to a bigger block cipher and solve some of those. Yes, we would want to, but it's not that easy. I mean, like to move the entire community and like the applications to use another one and to standardize another one. You can see how long it takes to standardize one. So we want to see what we can use that's available, that's already standard to solve some of those problems. Okay, so one of the problems, for example, specifically for AES-GCM, is that the GCM is double account remote. It's both a block cipher, as we said, for authenticating and for confidentiality and authentication. So the IDs are only 96 bits, and it becomes a bigger problem for trying to avoid non-reuse or the ID reuse. And if you reuse it, you can lose authentication completely, and you need the pairs of plain text that were reused. So no reuse means that we either use random IDs, which gives you like bounds of like using at most 232 messages per key. Or you can use deterministic IDs, but we will see in some applications that this is very challenging. So if we use random IDs in an application like transport encryption, for example, we have big fleets of device, you can run out of like per key, out of 2 to 32 messages in about 2 seconds. So imagine rekeying every 2 seconds. That's a big operational burden and very risky. Because if you cannot do it, then the problem, as we saw, reuse is catastrophic. For something like AWS Key Management Service (KMS), like if the user managed keys, which we call them here AWS KMS key, they are used to encrypt other keys or to encrypt small messages, and so running out of 2 to 32 queries can happen in a matter of a week. And so imagine KMS managing like this huge number of keys for accounts, having to rotate them or rekey them weekly, for example. That's a big burden. But then the other alternative, which is deterministic 96-bit IDs, has its problems too. So for example, if we go back to the transport problem, we have like a big fleet of devices, and we need to now like increase the ID deterministically, like monotonically increasing. Then you would have some part of it that's a counter, and maybe the counter would be 64 bits, so that you have like 64 bits messages before having to repeat. And but then the identifier is only 32 bits, managing a large number of devices. When you bring in more devices, you take out some. This is a big operational burden, and also like you have to in those cases you have to keep a state and to prove the IV uniqueness for FIPS or otherwise, like for operation. That's also a bit like overhead and adds a lot of complexity. So now what? So it has been proposed in some cases, and in AWS it has been used also since 2014, a method for, instead of directly using the key, the main key, to be the key of AES, no, it's used with a first nonce to derive another key, and then that key becomes the key of AES with the second nonce. And so that reduces like the collision on the pair, like with the same key, you're using the same ID. And so KU is derived for each new invocation. So every new message, you have a new nonce one, and then the key is actually derived for every new call to input. Okay. So one example of those was proposed by Filippo Valsorda recently, and Filippo is also maintaining the Crypto library. It's called AES-GCM. And he proposed using HKDF that's CMAC-based in counter mode. And so there are two invocations that's to derive the key. Two invocations to CMAC, but they simply boil down to those two operations, each calling AES once, because the input is one block. And the input is like the first part of a 24-bit nonce, 24-byte nonce, sorry. And those are the two calls that happens on every invocation to derive a new PKU. But there is like the innate part of it is that the main key is used to derive K1, and this is a detail in CMAC. Like if you go to the CMAC specs, you'll know what's K1, but it's basically derived this way. And so then there's this new key, and then there is the second part of the nonce is the ID of AES-GCM. So this part here is what happens on every invocation. And so the motivation for this is that we will see that this component is just certified, but it's also using the same Blockcipher for key derivation versus other key derivation methods as the AES-GCM. Usually, like, when you think of that, not only in software but in hardware as well, if you don't need to use more components, then your circuits are smaller. But like I'm working with AWS LC, and we will see some performance numbers, like performance gains in doing it this way as well. So yeah, here I'm saying that those are basically two invocations of CMAC AES, and because of the input block being of the input to CMAC being only one block, it's only one AES operation per side of the nonce. Sorry, per side of the key. Like this is a 256 bit key. There's 2 bytes. Okay, so key commitment. What is that? So in some situations where, for example, in storage, where an attacker can have some data stored as an encryption, some ciphertext stored as an encryption of certain message, but he has control of the keys. So like when sent for decryption, it can be decrypted to one user with one key, and then decrypted to another user with another key. And both decryptions are valid, like the plain text makes sense, but it's not the same. And that's a problem because AES-GCM is not inherently resistant to that. So like it doesn't guarantee that you can And it doesn't prevent decrypting as a valid ciphertext, and of course the authentication is correct, to two valid plain text used under different keys. So the solution to that is to actually bind the key to some of the inputs, at least the nonce, and put a stamp on it. So that there will be another value that we will see stored in the output with the ciphertext to bind the key to the inputs. So recall that those are the two functions we define under AES schemes, which is encrypting with a key, a nonce, authenticated data that doesn't need to be encrypted, and plain text that's encrypted, and producing a ciphertext that includes the tag, like the authentication part. And decrypt takes the key, the ciphertext, and the authenticated data, and either reproduces back the plain text or nothing if the authentication fails. So there are different notions for key commitment. So, and basically key commitment wants to guarantee that you cannot, for the same C, like same ciphertext and authentication tag, you cannot obtain you cannot obtain the same ciphertext when you encrypt with differences in the input. So for 4KC is the name of one notion, the other ones are sway them here. The first one is on is when you have two different keys, but the same nonce and any pairs of additional data and plain text, and then you produce a ciphertext. The 4KC notion of key commitment guarantees that you will not be able to have two different keys that will satisfy the same key commitment. And then it progresses until this is the most sophisticated one, which binds the key. It commits the key not only to the nonce, but to also the inputs, the additional data and plain text. For the purpose of the AES schemes, usually the nonce, especially if it's like random, is stored with the ciphertext. So for all purposes, those three notions boil down to being not distinct in terms of key commitment. I will tell you more about how this is done. So this is, in our work, that's what we've done, is we added the key commitment to Felipe's XAES 256-GCM by also using HKDF based on CMAC in counter mode. And so we, in this case, to bind the key to the entire nonce, it actually boils down to two invocations of CMAC, but each of them has the entire nonce's input, so those are actually two blocks of AES. So that results in like 3 AES calls, because the first part of the input is common to both, so it can be reused. And that produces a 256-bit key commitment that gets prepended to the output and stored with the output. And we will see, like we talk a little bit about the analysis of that key commitment. So putting them together, this is the part for the key derivation, this is in the original scheme. This is the part for the key commitment, and also this in it is called once per main key to produce K1. And then the rest is called every time you invoke the scheme for every encryption. So if you mentioned FIPS is the Federal Information Processing Standard. FIPS 140-2 and the newer 1-3 are programs that validate crypto modules. It started more around hardware, like especially like HSMs, hardware storage module, and that was, it talks about, like, it ensures that the cryptographic module is operating correctly, so there's a lot of tests of the algorithms to make sure that they are producing the right answers, and if they store keys, that they are tamper-proof. But they started like maybe a couple of decades ago, more like applying to software modules as well. So that's what Matteo was referring to, that AWS LC, which I mentioned quickly, is a FIPS validated software cryptographic module. And also OpenSSL had gone through the FIPS validation and stuff like that. So it basically says that those modules can be used for mostly it's part of the assurance for US governments and other governments like in Canada, and also there are similar programs in Europe that this module operates properly and can handle sensitive data. So Key derivation methods like in counter mode and CMAC being one of the pseudo-random functions that can be used in them is a FIPS approved algorithm. So this component is, and AES-GCM is a FIPS approved algorithm for authenticated encryption. So that makes both components, like you can argue that you're using FIPS components to build the scheme. And also, we use the same components here in key commitment. FIPS doesn't define a key commitment algorithm, but if that happens at some point, we can also argue we're using a FIPS approved component here for key commitment. So yeah, that is basically what I was talking about, and this is from the standard, this is special publication 800-108. This is how a key derivation function counter mode is defined, like there is a counter that's implemented here. And basically, both in the key commitment and in the key derivation, we're using only 2 invocations. The difference is the size of the input that goes in. For data limits, so we had seen before that with random IVs, you can at most do 2 to the 32 invocations for the same key. Now in our analysis, with AES-GCM, we can do up to 280 invocations for the same main key, assuming random nonces before you reach the collision probability of 2 to the minus 32. For the message length, in our analysis too, you would find that we didn't codify the limit that's already put on AES-GCM, which is the number of the maximum length of a message before you run out of counter space internally in AES counter. And so this is about 64 gigabytes. But in our analysis, we added that if your application is more restricted than that, and you say you're enforcing per key not to encrypt more than X bytes, then your maximum message length using the key commitment that we're using and using XAES, you would not be more than X over 7 bytes. And you can see the details in the minutes. For the security analysis of the key commitment part that we worked on, you can see proofs about how if you use the 4KC notion, that means your nonce is constant, you will not be able to find 2 keys that produce the same key commitment with this probability on the collision, which is like if the number of queries or number of attempts is much less than 2 to the n is the size of the block cipher, so it's 128 in this case. Then your probability is of this order that's intuitively, but the proof shows it's of this order. So if you can think of it, that you would have probability of 2 to over of 1 over 2 or q over 2 to the 128 before you can actually find a key commitment that gives you with different keys that can apply with the same nonce. So we will talk a bit about performance numbers. So if you go to AWS website, AWS Live Crypto, it's an open source, and it's a fork of boring SSL, but we've taken it through FIPS validation, and actually we've done the 3rd validation, like it's now 3.0. You will not find the XAES, but I worked on it to see how it can be plugged in. At some point we will put it out, but I will give you the numbers based on putting those components in AWS SC. So those are numbers measured on C6i instance. That's an Intel Xeon 3275, I think. That's a powerful Intel processor. It's Ice Lake, I believe, and it has AVX512 capabilities. So the AES-GCM in it is highly optimized. It actually processes up to 16 blocks in parallel. So that's why you can see that for AES-GCM, I will talk a bit more, but I will tell you first here that when you're doing encryption, even as some of the, for small plain text, even as they are doubling, the microseconds that are taken are not doubling because it's highly parallel. But I'll tell you what goes into the numbers. So first, this number of microseconds for AES-GCM is because what happens first in AES-GCM, you have a key scheduling of the key, and then an encryption of all 0 inputs, and then there is, because it's highly parallel, there is a pre-computation of the components that will be used in authentication, which is the G-hash function, the G in GCM. And so this happens in initialization, but on the other hand, when you're doing XCS, the initialization is only those two parts, the key scheduling of the key and encryption of all 0 input. That's why it's less. But then what happens is that on every invocation for XAES, you have to do all those because you're producing a new KU. So you do the things that you would do for AES-GCM. So that's why there is this constant overhead in XAES compared to GCM. Almost constant. And also you add to it the AES computations here. Those are numbers for XAES with key commitment, which is what we did. And so the overhead is also almost constant, but it includes those 3 AES operations in addition to the previous ones. So that's putting it, but as the plain text gets larger, yeah, that's the process. You can see that the overhead of XAES observed, of course, starts to vanish when you reach 1 megabyte. It's almost you don't see it. And this is in comparison when you use HMAC AES. So this is also done in AWS LC, but it was way before AWS LC, like since 2014. HMAC was used as the PRF in KMS, Key Management System of AWS, to also derive the keys, because this problem was identified early on, that we would run out of message space very quickly. But using AWS LC components, we can see that the overhead HMAC is larger because SHA-256 invocations are much heavier, about 10 times heavier than an AES-1. But also, like, eventually the overhead, you wouldn't see it without the plain text.
Nevine, sorry to interrupt.
Yeah,
to wrap up.
I'm done. Yeah, sorry, I want to thank you. Yeah, this is the similar numbers, but on another instance, which is ARM-based. But yeah, I think that was all I wanted to show you. I don't think there's time for questions. I don't know.
Yeah, I think we will
We're slightly over time.
Yeah.